Welcome to Happy Maths Hour. We will be introducing an extraordinary person I've just found out about. We're going to show a video which you're going to enjoy enormously. I was very entertained and I'm looking forward to seeing it again. Over to you, Toni.
Hello. We're going to introduce you to a friend of mine. We are going to be doing Mobius strips.
I'm feeling itchy, Toni. I'm feeling itchy.
The bugs. Yes. Yeah. Look at these now. This is an Escher wood graving and print. And he wants to show the peculiarities, really, of this Mobius strip, which will be revealed this evening. And you'll see how some of those bugs seem to be on the sort of what's top or bottom, others on the bottom, one side, the other side.
The outside.
Where are they going? Can you follow them round? And we'll help you to do that in other ways. But I think that's a very good starting point. Here you see Tadashi holding up a Mobius strip. And in a minute, we're going to see a video made by made at Ames by Tadashi. Now, he is there in the lecture theatre at Ames, the African Institute for Mathematical Sciences. Tadashi is his first lecture on geometry and topology. So you will be learning a bit about the maths of Mobius strips today.
I should just mention Tadashi is from Cambridge and Harvard. He is based in Cambridge, but for this coming year, I think you're at Harvard. Is that right?
Yes. Good.
I think he's taking off his shoes.
Hi. We have all seen a Mobius strip, haven't we? Mobius strip? Ruban de Mobius. It is the strip that you make by twisting and gluing the ends of a strip together.
Right, now can you see my little bug? He's moving on this railway track. He's going round on the inside of this track, right? And he can go all the way around. Keep going, little bug. It's not totally easy to just show you, but you can imagine. You can just see this ordinary loop. Now, this isn't a Mobius loop. The other thing he could do, he could go round on this grassy track on the outside. Now, this grassy track, right, it just goes on, and he would just keep going round and round and round. And this grassy track is on, and he wouldn't ever get onto the other track inside, which is no grass on it. Well, I'm going to see what happens when we make this into a Mobius strip. I'm going to just cut it and just now you can see the two railway tracks inside and outside. Now I'm going to change the points. Now that's a very normal thing to do with railway tracks. Very unusual, I suppose, when it comes to having these tracks on a Mobius band. But I mean, why not? I mean, we'll just see how that affects our little bug. But now you see we've changed the points. And so now she's going to carry on this track. Right, so here she goes. And I'm going to keep moving her. And she's moving, 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 moving. She's on the track that doesn't, at the moment, that doesn't have any grass, at least she was. Now she's going to where they changed the points. And what's happening to her now? All right, little ladybug. ladybird, you are on the grass. So switch from one surface to the other. So how many surfaces have we got here? We had two. We had one side and the other side. She's still moving along. She's still moving along. There she goes. Oh, she's getting, she hasn't, I know that she goes by electricity. I think she goes by Toni power, actually. Here she's going. She's still going. Oh, she's a long way on. But what's going to happen very soon is she leaves the grass behind. Look, and she's on the track now. It doesn't have any grass on it. So, well, what happened? She's on a Mobius band. What was two surfaces has now become one. Okay, so it was an inside and an outside, but now it's a Mobius band with a twist in it, where we changed the points. Where was that? Here we go. This was where we changed the points. What effect did that have? Made a single surface. Okay, shall we go back to the lecture from Tadashi, to the video?
Mobius strip has only one side and all that. You know this, but let's try something potentially new. Let's cut the Mobius strip in half. First, I'm going to make an ordinary strip. It is just straightforward strip. Okay, I didn't twist. It's not twisted. If I cut this strip along the center line, what's going to happen? What's going to happen? Yes, it's going to, I think, fall into two parts. And so it does. Okay. Now, let's make a Mobius strip. I do that, but instead of gluing like this, I twist by one. Well, some people call this half twist, but we shall call it one twist. Okay? So one twist by 180 degrees, not 360 degrees, but 180 degrees. And I glue the ends. So this is the classical Mobius strip. His name is on the blackboard. What happens if I cut it along the center line? Any takers? Yes, what's your name? Absalom. Absalom. So what's your guess? It will form two entangled strips. So you get two strips, but unlike those two that fell apart from the ordinary strip, they'll be entangled, he says. Any other takers? Any other guesses? Is Justin here? I met Justin a moment ago. Yeah, what's your guess? It will be the same. So two strips, and it will separate into two, and they'll fall apart. Huh? So they'll be entangled like this, but there'll be two of them entangled like this. Okay. Any other takers? So the same guess twice. Any other guesses? You should guess. The first lesson or the 0th lesson in mathematics is that you should always begin by guessing, if possible, in public. So that you are committed. Now you are interested, your stakes are high, and you have to find out what's going to happen, and you learn much better. You see, you're going to spend a year at things. You might as well learn this much rather than this much. And the way to learn this much is to guess, and to learn from your wrong guesses, and then build on your right guesses. So, any other guesses? Huh? Yes.
Tony,
two parts will fall apart, so there will be two parts. Okay. You had a guess. Same thing as those. Okay. So we have any other guesses? Any dissent? Okay, shall we do that? I'll start cutting the center line, and probably I should be singing a song as I do this. I'm cutting, and I'm going all the way around once. Yeah. I'm about to finish cutting. Ready? I finish. And I have a single strip. Very interesting. How did this happen? Now, I'd like to ask you, and please answer honestly, who has seen this experiment before? Please raise your hands. Who has seen this before? Some of you have. Good. Okay. You see, there are people who have seen this, but they may not have seen the next one. How many twists are there in this strip that we just obtained? In the initial Mobius strip, there was one twist. Okay, we counted that as one. How many twists? Okay, let's ask, who thinks it's not twisted at all? Zero twist. Okay, good, brave man. Who thinks it has only one twist, so it's the same thing as the original Mobius strip? One. Two twists? Okay, that's the one that most reasonable people go for. Congratulations. And the logic is actually not too difficult to justify. You see, suppose that this is the Mobius strip. Just the front of the Mobius strip, it goes and then twists in the back and comes back. Okay? And we are cutting it like this along the center line. And what happened is that, you see, if this were not twisted, as I cut this part, will go back and will connect back to the same part. Yeah? And this part will go back and will connect back to the same part. But because it's twisted, this part, which goes in the back, comes back up, but instead of connecting here, gets twisted and connects to this side. And this side, which goes back, when it comes back, gets twisted and gets connected to this side. Okay, so the entire thing gets connected. And you have gone around the strip twice when you do this. This has exactly twice the length of the original strip. So if the original strip was twisted once, well, we went around it twice, so it should be twisted twice also. Good. Who thinks it's twisted 3 times? 4 times? Some people back there. 5 times? Anybody courageous enough to say 5? 6 times. I don't have 6 fingers on my hand. 6 times. Okay, so we give up. How shall we count this? What is your name? Huh? Sarah. Can you come upstage? Okay, so Sarah, if you can be my assistant, thank you very much, and hold this bit of the strip. And I'm going to hold the strip like this. Okay, and please don't move, even if there's another fire alarm. Now, this way, can you raise your hand a little bit? This way, you can see that all the twists are on the upper half of the strip, and the lower half of the strip is not twisted at all. So in order to count how many twists this has, I'm going to, don't move, cut the lower half, which is irrelevant, which doesn't matter, and then start untwisting the top. How many times do I have to untwist in order to get it straight? That's the number of twists that this strip has. Okay? So, how many times? Don't move. 1. It's still twisted. 2. Well, many people voted 2, but it's still twisted. That's very interesting. 3. Look, it's still twisted. Finally, 4, and it's straight. 4 twists. Thank you very much. We applaud, Sarah. Why 4? We thought, well, that was logic. We had 2 twists because Mobius strip itself, the original one, had 1 twist, and we went around it twice. Once, twice. Why not 2? Why 4? Where do those extra 2, 4 minus 2, extra 2 twists come from? Here is the beginning of a suggestion. Suppose that you have, again, an ordinary strip like this. Like that. I just closed it. How many twists does this have? Obviously, it's 0. Now, let's go around it twice, like this. Do you see what I'm doing? I just went around it twice, but without twisting the strip. I just went around twice, but I didn't twist the strip locally. How many twists does this have? I just did the double of the 0 twist. Does it have 0 twist? Actually, it does have some twist. Look. So just by going around the double cover is the technical term, but going around double of the 0 twist strip, you get some twists. Locally, this is not twisted, but globally it is. Interesting. That's where the extra 2 twists come from, because in fact, when I undo it and try to untwist it, it turns out that it's twisted twice. Okay, so just by going around twice, even without any local twist, you get those 2 extra twists, and those 2 are added to those 2, and you get 4. Something to investigate. Let's now try something else. So far, we have been cutting all the strips along the center line. But suppose that I'm not very careful. I miss the center line. Let's cut the strip along the 1/3 of the line. You know what I mean? So 1/3 of the distance from this side. In this case, we have that and that. And I'm cutting it along somewhere here. Okay. I go up. Now what's going to happen? Any guesses? What's going to happen? Huh? You have some opinion. Go ahead. 4 strips. That's very interesting. 4 strips. 4 strips. Okay. Any other guesses? Huh? 2. 2 strips. Okay. Shall we vote on the number of strips first? Who thinks there will be a single strip? After all, that's what we got when we cut the Mobius strip along the half line. Do you remember? Along 1 half line. So one strip. So several takers. Thank you very much. 2 strips. 3 strips. Good. 4. There was some taker. 5. How about the 0 strip? Okay. So let's see what's going to happen. People who said 2 strips or more, 2, 3, 4, 5, and so on. Are these strips going to fall apart, separate, or not? Why? Why do they get? What's the word? What's your name? Huh? Hidis? Seriso. Seriso, what's the word? If you want to express what you're thinking, they don't separate, they get what? Yeah, let him say it.
They make something like a chain.
Something like a chain. So it's very heavy. No. What do you mean? They get? Well, this is your opportunity to learn a little extra things. So what's the expression? They get? Our friend here used the word a moment ago. Were you paying attention? That was an opportunity to learn. Entangled. Say that. Entangled or linked. That's a more technical term, but entangled, linked, and so on. Okay, while I'm discussing this, I went around once, but look, you see, I kept cutting along the 3rd line, but I didn't come back to where I started. I came back on the other side. In other words, I kept going, and it got twisted in the back, but when I came back on this side, not on the left side. Why is this? Do we all understand it? Yes, we do, because you see, this line, if the strip were not twisted, it was an ordinary twist, would just connect back to the same side, but you see, it is twisted. So this line, which is on the left-hand side, gets twisted and connects on the other side. So we have to keep cutting. We have to go around twice. So let's keep cutting again. Have you made up your mind? I'm about to finish cutting. Huh? What? Who says what? I keep cutting. This is getting more and more complicated. What's going on here? I have no idea what's going to happen. Okay, are you ready? I'm about to finish cutting. Nothing up this sleeve, nothing up this sleeve. Oop. Beautiful. What happened? Do we understand this at all? There's a long strip and short strip that are interlinked. How many twists does this one, short one, have? One. In fact, you can kind of see it. Yeah. So do you recognize this? This is just a narrow version of the original movie strip. One twist movie, just narrow. How about this long one? How many twists does this have? We should count, but it turns out to have 4 twists. So this too is a narrow version of something familiar, the result of the half cut. And they're interlinked. Why is this? In order to understand this, let's perturb the parameter. That's what we say. What do I mean by perturbing the parameter? Well, we cut it along the third line before we cut it along the half line, but we can cut it along the line which is at the distance d from the edge. Okay? So the half case corresponds to d equals 1/2, and 1/3 case corresponds to d equal 1/3. But I can make d any number between 0 and 1/2. It doesn't make sense to make it larger than 1/2 because I will be on the other side. Okay? So what happens if d is 0? Yeah, I'm just sliding the scissors along the boundary of the movie strip. I'm not doing anything, essentially. What happens when d equals 1/2? Well, it's exactly the single sort of half line cut that we mentioned before. But in between, what's going to happen? Well, the cuts look like this. Okay. Let's think about where this strip goes. This part of the strip, left half of the strip, closest to the boundary. Well, it goes in the back, and then when it comes back, well, an ordinary strip would make it connect back to here, but the movie strip twists it and connects it to this part. So this portion and this portion are connected to each other. And similarly, when I go out over here and come back, instead of connecting back on the right, Mobius twist connects it back to here. So this is a single strip. On the other hand, what about the part in the middle part? Yeah, so when it goes out, it comes and it gets twisted, but it gets connected to itself. So this is its own component. Okay, now we understand what's going on. You see, we did it in the case of d equal 1/3, but let's make d very, very small. When we make d very, very small, what we're doing is just caressing along the boundary and not doing anything. So we get this middle yellow piece, which is getting fatter and fatter and fatter, and eventually you get the original movie strip. Yeah? Or conversely, if you make d larger and larger from 0 towards 1/3, we are just making the original movie strip narrower and narrower and narrower until it has, what's the width of the middle piece in the end when I'm cutting at d equals 1/3? No. No. If this is 1/3, this is also 1/3. Thank you. So that's also 1/3. Okay. So what we have here, the short one, is just the original movie strip whose edges have been taken away. That's why you get a copy, topologically the same copy of the original movie strip with one twist. Do we understand this other one? We do, because that one, the long one, corresponds to the pink portion. You see, here, we examine the case when d is 1/3, but let's imagine the case when d is almost 1/2. That means that this yellow part becomes narrower, 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 okay? And as D converges to 1/2, this yellow part collapses to a single line. But we know what happens when I cut it along the single line. When we remove the single line, we get a long single strip with how many twists? 4 twists. So instead of cutting it along a line, let's cut it along a fat line. You know what I mean? So let's remove the middle portion, but what remains on the side is exactly topologically the same as the case of the half cut. So this one, in other words, this long piece has also width 1/3, and it is topologically a copy of the half cut. So that's why we see this familiar 4-twist Mobius strip and this familiar 1-twist Mobius strip. Why are they linked to each other? Do we know? The gentleman who yawned in the back. So why are they linked to each other? Why shouldn't they fall apart? In order to understand that, let's look at the central piece again, this piece. And let's represent it by a single yellow line. I'm going to draw it here. And let's see what the other one is doing. So this yellow line is actually doing something like this in the back. Okay? How is this pink part positioned with respect to the yellow? Well, for a while, it's running on the left of the yellow, if you like. Is it going to join up to the original bit? No, it's going to be twisted and then join up here. So I keep going. And now, is it going to be joined up to this part? No, it gets twisted again. It crosses over. And you see here, the pink strand goes around the yellow center once. And that is exactly the link that you see here. So we understand a lot about this. Okay, let's see what we get if you cut it almost at D equals 1/2, but not quite. What do you expect? It's a revision. D is almost 1/2, but a little less than 1/2. What do you expect? Yeah, long 4-twist. And this is the result, it turns out. You see, we see almost exactly the same thing as in the first experiment, the half cut. But here, there's a very, very thin version of the original Mobius strip, which is linked. This very thin one is the yellow
Take that one
in the center.
away.
Okay. In contrast, if D is almost equal to 0, what do you get? Yeah, you get almost the same thing as the original Mobius strip. Almost, you didn't do anything. So this is the result. You see, you have practically the original Mobius strip intact, but look, there's something linked to it. What is this? Well, think of it this way. Think of the Mobius strip, but think of peeling off, scraping off the boundary, and boundary comes off and gets linked to the Mobius strip itself. And it is twisted, this boundary bit, which is the pink part of the picture, is twisted how many times? 4 times, thank you very much. And it's a single circle. From which, by the way, we discovered that the boundary of a Mobius strip is a single circle. Am I making sense? No, I'm not making sense. I didn't understand what I meant. So, what do I mean? This is an ordinary strip, not twisted. What is its boundary? Well, boundary is the mathematical term for edge. Well, there's this boundary, and there's another component of the boundary, this boundary. So there are 2 separate disjoint circles. The boundary of an ordinary Mobius strip, is 2 circles. Okay. What about the boundary of a Mobius strip? I don't have a Mobius strip anymore because I cut them all. Please ignore this one, but it is in fact the boundary. This is a Mobius strip. What is the boundary? You go along the boundary, and then to your surprise, you see that the entire boundary is connected. there's only one loop. Who's not convinced? Please raise your hands. At least half of the class should be not convinced. Are you all convinced? You're a bunch of geniuses. Okay. So movie strip has a single boundary circle. Okay. So that's what happens. Okay, we understand everything now. Let's go back and finish all this by a little revision. You understand now what happens when you take a movie strip, one twist, and then cut it along the center line, right? What happens? Huh? Sorry? No, a single movie strip, one twist, and I cut it along the half line. What happens? What's your name? Huh? Xavier. So what happens if you take a movie strip and cut it along the center line? Yeah, that's a single strip with how many twists? 4 twists. Yes, we understand this. Yeah, of course. We all know this because we are very clever people and a bunch of geniuses. Okay, so this is what we get. Oh, what happened? What happened? We got 2 components. Huh? What? Huh? Xavier, what happened?
That's what I told you. Thank you.
Eh? So people back there have an opinion. So what are you saying? What did you say? Say that again. Say that again. I twisted the original strip twice instead of once. You're saying I cheated. Respected teacher. Do you think you should disagree with the teacher? Yes, you should. Yes, that's what I did. I twisted it twice. But that's interesting, right? Because first of all, some people were taken by surprise. But also, exercise or research project. Develop a complete theory for what happens when you take a movie strip that's twisted, let's say n times, and cut it along a half line, or cut it along the distance d line. What's going to happen? What's going to be the result? There should be a very clean, complete description, and that's a wonderful thing to work on. Let's take a break for 5 minutes.
So there is Tadashi. Just talk about some of the things that he did, because I think he showed us good teaching, didn't he, really?
That's the thing. I mean, I love the Mobius strips, and I learned a lot about Mobius strips, but what I loved was the comments he made about should you question your teacher, and earlier on at 3.5 minutes, starting there, he made some very wonderful observations about the skills that you need to be a mathematician, and they aren't.
But he was saying that if you're learning, you should make a guess. And he said, you know, and preferably in public.
You're committed.
Yes. And then he said something interesting. He said, if you you can build on your correct guesses and learn from your incorrect guesses.
You learn more from your incorrect guesses.
Exactly.
You learn from your correct guesses, but
yes,
and always build on your correct guesses, not just go, I got it right, that's it, I can rest on my laurels.
Yes, yes.
That much. There's just a few seconds when he said all those things, and it's like gold, diamonds. It was amazing.
And at the end there, he did cheat, and he did it for effect. But as a matter of fact, he is a magician. He's a great showman, and he puts on the most wonderful performances, like you, Caroline. And he is a magician. He does magic. And And he can convince you that black is white, really, but he wasn't trying there. He really wanted you to spot that he twisted it twice, and he set the students there a task, which was to see what happened if they twisted it 3 or 4 times and still went cutting along the middle, and what sort of result would they get. And of course you could guess, and you don't need any expensive equipment, you just need some scrap paper and a sticky tape to join it up and make your own Mobius strip, and you can twist it as many times as you choose. The other thing he showed us was he didn't actually use the word limit, but what he was actually showing us is that distance from the edge. First cut that wasn't in the middle was 1/3 of the way across, and he called that distance from the edge D, which was, as I say, to start 1/3. And then he showed us what happened if he made D small and what happened if he made D nearly 1/2. Now, if D was 0, of course, nothing happened. You just sort of skimmed the edge and nothing happened, really. You went all the way around, but you didn't cut anything off. If you made D very small, all you did was cut off the tiniest thin little boundary, and you were left with your original strip. But if you made D nearly 1/2, your original strip became very small, very thin rather, and you had almost the effect of having a cut in the middle, because you were cutting near the middle. And so he showed this way in which we often think in mathematics. Well, we saw what happened when D equals 1/3. Can we imagine what would happen as we change D? I think at one point he called D a parameter, but I think he only used that word once. In mathematics, a parameter is something that determines how the whole character of something. It's really important, but it's something that you can change, and you get something different if you change it. And so that's what he did for us. And there are many more questions that you can ask about the Mobius strip. But what it's often used for is an introduction to a whole new area of mathematics. It's a big subject, isn't studied at school. It's studied a little bit at the undergraduate level, rather more at the graduate level. And there's research going on into topology. What he showed was that things about the surfaces and the boundaries, which we'll come back to. But I'd like to say something about Tadashi himself, okay? As you could guess, he's Japanese. He speaks fluent English. He speaks about 12 languages, because he was first and foremost, a linguist before he became a mathematician. He specialized in languages. Although he's Japanese, he went to school in France, and he's fluent in French, of course. But he then did classics and was a lecturer in classics at the University of Tokyo, before he gave all that up and started all over again to study mathematics and physics. And he's worked in maths departments and physics departments in the UK and America as a professor. And it was wonderful to have him here in Cambridge, but now he's at Stanford. So this film was taken in 2014, and he visited Ames and gave lectures on several occasions. So we'll show another film that he made, which I think you'll enjoy, a little bit different to today's. We'll do some more on Mobius strips next week. And I'll just remind you of my bug, and that's what you saw earlier. And then this is the bug on a Mobius strip. And you can see there where the points were changed. Now, I want to just use that to talk about the topology. So can you see that where in this there were two edges to that strip, Caroline? Two edges, each of them an ordinary circle. When you go to the Mobius strip,
two edges and two faces, right?
yes, surfaces, yes. Now, when you go to the Mobius strip, you've only got one edge. And so if you ran your finger around the edge, you would come back, you'd stay on the same edge until you came back to where you started. And similarly, with the bug on the railway track, you can see there's one surface. So the twist has made quite a dramatic change in this strip. It's changed it from something that's had two edges and two surfaces to now being something with one edge and one surface. It's amazing, isn't it? And
it's fascinating. I love Mobius strips.
Yes, and so there's a Klein bottle. I'll find some pictures of a.
You gave me a Klein mug.
So we'll get some pictures of Klein bottles, which is like the Mobius strip, but going. See, that is only a surface. It isn't three, although it is spread around in 3 dimensions. It has only got a surface which is 2-dimensional and an edge which is 1-dimensional. It isn't 3-dimensional. So next week we'll look at the 3-dimensional equivalent, which is called a Klein bottle. So also we'll look at some things that are topologically equivalent. Now I actually don't know much, hardly anything at all about topology, I have to say. And I actually only know what children in school could easily appreciate and learn. It's the fact that topology is about surfaces and it's about holes, shapes which have holes in them. And what difference does that make to the mathematics? How do we analyze it mathematically? Anyway, we'll explore it a bit further because there's some very interesting pictures and ideas there. But because we were talking about AIMS and the African Institute for Mathematical Sciences School Enrichment Center, which is one of my babies, something I've been working with now for 18 years, I want to just share a few more ideas about it. So there's Africa. It's huge and it's got so many people, but African countries are quite poor and it hasn't got any of the advantages, very few of the advantages. It's got many advantages that we don't have in Europe. Such a beautiful continent it is. But what AIMS is trying to do is to enable Africa's brightest students to flourish. And our slogan is, the next Einstein could be African. And we want them to be independent thinkers and problem solvers and innovators. And we want them to be capable of making Africa grow economically. And so building its scientific and educational and economic self-sufficiency, that's what we see our AIMS graduates, as they get older and more experienced, going back to their countries around Africa and making a contribution, helping to build their own countries and research in their countries. And I'm working with teachers in South Africa. And what keeps me going is this idea that education helps people to help themselves. It empowers people to fight poverty and inequality. So there are some quite boisterous, naughty-looking little children. Children are wonderful, same the world over. And they're in a school, and there's a township, a typical township. Millions of people in South Africa live in townships and shacks like those houses you see there. And I want some of those children to be educated by the teachers we train and to get such a good education in school that they're going to be able to go on into jobs where they're going to be able to make a contribution to their country. That's what we're trying to do. We're trying at AIMSEC to bring new hopes and new skills and new horizons for education in Africa for children like that, so they can fight their own way out of poverty. We can't do it for them. In fact, the teachers are the people who are so important. Now, what I found when I went to South Africa in 2003 was I was told by so many people that there was a crisis, that their maths and science in schools was about the lowest in the world at that time in terms of international comparisons. But the teachers are dedicated and they do a great job and they work hard and work cheerfully on really poor conditions. So what we do is we try and give them the training that apartheid denied them. And they train other teachers. So we train, AIMSEC trains some teachers and they train, in their turn, they train other teachers. And they empower them and the learners to rise up out of poverty. At least that is our ambition and our hope. And we've got some success stories and we are hoping to hear more as time goes on. And so we're building a network. It's a network of communication. It's a network of people. And it's a network of schools, of course. And it's what we use, what we need is resources. And so we share those resources. So we have a cascade model to reach many schools and many learners, particularly in the rural areas. We want to empower teachers to improve mathematical education in their own communities. It's not just in South Africa, this network, it's across Africa for mutual support, for people to learn together and to share information and the resources. I've written e-resources there because we share them on that website. You see a link there. That's how we share the e-resources. And we talked other weeks about how we are sharing resources. And I'm a lifelong learner. I've been learning for a very long time as I'm quite old. And I'm committed to continuing to learn. So I certainly think that teachers need to be learning all the time while they're on the job. And so we've come up to 6:01, and there's another picture of a Mobius strip.
That's a really nice one, Toni. It's very clear.
Well, I found it because it looks like railway tracks again.
Right, yeah.
But it doesn't have the number of sleepers it would need on a railway track.
No,
but
it doesn't have a Mobius bug either. I love your Mobius bug.
It doesn't have my little ladybird here. But I think we've introduced the idea of topology. We've talked about AIMSEC, and I hope you've been listening, you've enjoyed it.
Thank you so much, Toni. I really, really enjoyed that. We'll go back to minute 3.5. Everybody, minute 3.5. The link to the YouTube is in the description. And there's such a valuable learning. It's not just for maths, it's for learning in general. It's so powerful. Thank you all for joining us. Temba says, great, good presentation, Toni. Indeed, AIMSEC is making good strides towards capacitating mathematics teachers, subsequently empowering teachers to skill develop the African child, giving the necessary 21st century skills. And this is somebody on the ground in Africa. He works for AIMSEC, he knows what's happening, and that's brilliant, that's beautiful. We want to preserve that. See you next week, everybody. Same time, same place. Happy Massa, and we will be doing more Mobius strips. For greater understanding and enjoyment of mathematics, the Maths Toys YouTube channel is brought to you by AIMSEC and the Aiming High website. In the description, you will find a link to our home learning guide for ages 4 to 18 and a teacher resource pack. If you find this video useful, there is a GoFundMe link in the description to donate to and support AIMSEC. The money goes to bursaries for professional development for teachers in disadvantaged communities around the world. Subscribe, comment and ding the notification bell to make sure you don't miss our latest activity.